myself. So I'm Faith Vandeput, and I am a farmer on Lopez Island, and I'm also the Agricultural Resource Committee Coordinator for San Juan County. So the ARC, the Agricultural Resource Committee, we have been over the last few years in this discussion where we've been looking at, in the face of climate change and increasing development pressures in San Juan County, we've really recognized the need for increased solar generation and also increased protection of agricultural land. So because of this discussion that we've been in, we teamed up with WSU Extension of San Juan County, which Kate Mikuluk is here with us, and she's kind of holding down the back end of the technology side of tonight. So thank you, Kate. And then also American Farmland Trust. So we collaborated to bring this panel together and to hopefully inform ourselves and the farming community about both the opportunities and points to consider when siting solar on farmland. So that's how we got here tonight. So we're super excited this is happening. We've been kind of working to put it together for a while. So we're going to start with Danny Madrone, and I'd like to introduce Danny. So she is the Pacific Northwest Policy Manager for American Farmland Trust. And over the last 40 years, AFT has advocated for saving the land that sustains us by protecting farmland, promoting sound farming practices, and keeping farmers on the land. Recognizing the conflicts between farmland protection and renewable energy development, AFT has recently turned its attention to smart solar siting program design and policies in New England, in New York, and in the Pacific Northwest. So thank you so much, Danny, and I'm going to hand it over to you.
Thank you so much, Faith. I'm going to go ahead and share my screen here. Can we all see that? Excellent. Well, as Faith mentioned, my name is Danny Madrone, and I'm the Pacific Northwest Policy Manager for the American Farmland Trust. We are the only national organization that takes a holistic approach to protecting farmland, and we're dedicated to saving the land that sustains us by protecting farmland, promoting sound farming practices, and keeping farmers on the land. AFT has 6 regional programs, and including the Pacific Northwest, where we've had a presence for 20 years. And many people may recognize AFT by our bumper sticker that says, "No farms, no food." And so I'm gonna provide just a very, I'm pretty much gonna set the stage for our other presenters and talk about some opportunities and considerations for solar on farmland. So why do we care about solar at AFT? And the prime reason is because climate change impacts farmers significantly. Drought, extreme weather, impacts on people who work the land are just a handful of examples of why solar energy is important to us, because we really need to address issues of climate change. And in 2020, only 4% of America's energy came from solar. And the expectation based on a recent report from the Department of Energy is that solar panels might produce up to 40% of America's energy by 2035 and 45% by 2050. So that's a huge increase. And Washington State, we had the Clean Energy Transformation Act that says that by 2045, 100% of our electricity is going to come from clean and renewable resources. And so why are we talking about solar on farmland? And so some research that the American Farmland Trust did for farms under threat shows that we lost nearly 100,000 acres of farmland in the past 2 decades in Washington, and 54% of that was our state's best land. Much of that was due to urban sprawl. You can see that in the map right there. It's at the edges of urban areas where people are moving and we're seeing development occur. But solar energy presents a new challenge for farmland preservation. And in this report from the Department of Energy, it says that 90% of solar by 2050 is expected to be utility scale solar development in rural communities. And also by 2050, some preliminary number crunching that was done by AFT shows that we can expect between 98,000 and 145,000 acres of land in the Pacific Northwest to be converted to solar. And agricultural land is flat, it's treeless, it's undeveloped, and it has access to infrastructure such as roads, making it a cheap and easy place to put solar energy. So when we're talking about solar on farmland, there's two approaches to that. What we were just what I was talking about in terms of some of the development on farmland that we're starting to see out in the eastern side of the state is front of meter type farmland. It's power that is generated and then sent onto the grid. It's not used on site. And it can produce some income from long-term leases of land. And these are larger installations. And generally it's for land that needs to be close to substations or utility infrastructure so that it can plug into the grid. And then the other option, which I think we're more interested here in this conversation, is the behind the meter installations for farmers. And so that's power that's generated and used on site. It can also be sent off site with bidirectional meters. So any excess energy that's not used can be sent onto the grid. There's cost savings for energy because there's cost savings for energy, and then there's also income that can be generated from excess energy, and that's with net metering. That's that bidirectional meter that's putting the energy onto the grid. And there's also the option to install batteries to keep energy to keep yourself off the grid. And these types of installations are generally smaller. And so I'm going to give a very, very basic introduction to dual use, which others call agrivoltaics. And Chad Higgins is going to go much more into detail. But this is essentially the integration of solar and agriculture. And it keeps our agricultural land in production while also providing the energy that we need and the transition from fossil fuel energy that we need. And it's solar installation that is designed specifically to accommodate agricultural operations. It's designed with agriculture in mind. And some of the research that Chad is going to be sharing shows that there's potential for solar integration with a variety of agricultural operations, cropping systems, livestock, apiaries, and pollinator habitat. And so solar, it does present an opportunity for farmers. There's that on-farm energy generation, additional revenue, potential production improvements with dual use, which Chad will tell us more about, and maximizing the use of marginal lands or land that has limited water resources. And a greater resiliency in the case of grid failure. So, when that power line does come down, as they do sometimes, you can still keep your operations going. But solar can also pose some challenges for farmers, and so I share this information so that people are aware of some of the barriers and challenges that are good to consider. And one of those is that solar is a long-term commitment. It's the life of a solar panel is between 20 and 30 years. It can be expensive. And it can also take land out of production, and there are also impacts for wildlife habitat. So if you're using your land for multiple purposes, farming, but also providing habitat, things like fencing around solar panels can have an impact on wildlife. And even with dual use installations, it can limit how your agricultural practices can change in the future. So you definitely want to be thinking really critically about your farm plan. It can complicate the future sale of property, and it could limit the ability to protect farmland with a conservation easement, because funding sources like WWRP will not protect land if it's being used for commercial energy production. And just some considerations, as you're thinking about, to the farmers on this call, as you're thinking about how and if you would like to integrate solar into your farming operations, is to think about what your long-term goals are and what your goals are for land tenure. Look at where your best land is on your property and how you'd like to protect that. And ensure that any dual use installation is built with current and future needs in mind. This can include spacing between solar panels, how you get your equipment around an installation, and also installation, how the panel itself is installed to make sure that soil is not being compacted, and also thinking about the eventual removal of the panels when they're no longer in use. Also ensure that any leases that you do contain provisions for decommissioning and returning the land to agriculture. There are some opportunities for grants and other kinds of incentives that can help cover the costs. And if you are offering another party to come and put solar panels on your land, consult with an attorney, because there's some things to consider. There's liability issues for both parties, and it's just good to cross your T's and dot all your I's. So just a few resources here. USDA does have Rural Energy for America, the Rural Energy for America program that has grants and loans available. The Department of Energy has a really cool guide for how farmers are going solar. The New York State Farm Bureau has also created a guide for leasing your land for renewable energy. And also Sustainable Connections is a local organization. They have a community energy challenge, which is focused a lot on energy efficiency, which we should all be thinking about as well, because that's less energy that's needed. But they also offer some technical assistance with accessing those the REAP grants and loans. And that's all I got for you. There's my contact information right there if folks want to follow up with any questions. But I think the meat of this this conversation is really going to be what Chad has to provide for us.
Thank you so much, Danny. That was a great overview. So one thing I forgot to say earlier is if you do have questions that come up, please, you can go ahead and use the chat function and put questions in the chat. And Chad's going to be kind of monitoring that a little bit as he talks. And if your question doesn't get answered, I'm going to be kind of pulling all those and we'll bring those into the Q&A at the end. So do utilize the chat function for questions. So now I would like to introduce Chad Higgins. So he is an associate professor at Oregon State University in the Biological and Ecological Engineering Department. And he leads the Nexus of Energy, Water, and Agriculture Laboratory, the new Ag Lab, whose research focuses on resource trade-offs and sustainability within agricultural systems. His recent work has focused on agrivoltaics, the mutually beneficial combination of agriculture and solar energy production. And this work has received national acclaim and was highlighted as #5 on the National Science Foundation's most impactful projects of 2019. So we're really lucky to have Chad here with us. And without further ado, here's Chad Higgins. Oh, and you're muted.
And tick off that Zoom bingo box. Thanks. Those are always slightly embarrassing, but I appreciate the introduction. I will also add that I myself am a hazelnut farmer, and I own and operate a 37-acre farm here in the Willamette Valley. And I'm a country kid through and through. I grew up in a dairy farming community in upstate New York, and I really come at this from an agricultural perspective, because that's one of the things I really care about. This is going to be a conglomeration, a summary of about 5 years of research that we've done from a multitude of students and I'll try to give the credit where the credit is due. I kind of watch over people and tell them what to do, but these are the folks that are doing the work and taking the samples and analyzing the data and everything, and nothing of this would happen without them. So thank you to all of my students and collaborators. So what I like to do when I talk to mixed groups, particularly those that are not familiar with ag, and I know everybody here is familiar with ag, but I usually start a talk in this way. And it's the laundry list of things that people are basically use to try to put ag in context. You know, there's a tremendous amount of water use. Latest OPCC report has you at actually 37% of global greenhouse gas emissions come from ag. There's already 10% of people malnourished, and yet we need to double production. So there's a two-pronged problem here. We need less of ag to have, you know, less to share the water and have less GHG emissions, according to some people. And according to the same people, we need more of ag to feed the world. And usually when I'm faced with these statistics, can you see my mouse on this screen? Cool. Usually when I'm faced with these statistics, I say you're missing one, is that 100% of the food you eat comes from ag. So there's a trade-off, and you have to make these decisions. Are you going to stop eating? No. We also know that there's anticipated changes in climate moving forward, and if we game out what those anticipated changes are, irrigation is one of the most effective climate adaptation strategies, as keeping food on for our people. And that on the global average, irrigated land is 2.7 times more productive than dry land. So there's going to even be more pressure on water resource in particular as we move forward into the future, because, you know, irrigation is going to be needed to make up some of those heat units that are coming towards us. I was actually, my colleague Alan Branscombe and I were talking about climate projections into the future and where new crops grow in new areas according to those projections. It's kind of an interesting talk. So anyways, what we're talking about today is agrivoltaic systems, and the idea is the following. There is going to be massive pressure on agricultural lands from solar, and Danny alluded to some of the reasons. But there's even more. You know, it's a disturbed ecosystem. If you're farming, there's likely no endangered species that someone has to worry about from a permitting perspective. Agricultural soils tend to be deep and loose, which makes pile driving the stanchions into the ground a lot cheaper. It's flat, it's sunny, and it's in temperate climates, which is really beneficial for the solar panels because they're electronic devices that can overheat. All right. And then Danny mentioned, you know, close to markets, pre-disturbed, treeless, all of those things make agriculture very desirable. In fact, the most desirable land for solar. And we'll get into even more of that in a minute. Ag had an 8,000 year head start on solar, so it already has all the good land for solar harvesting. All right. At the same time, there are, you know, the reactionary question to that is like, all right, but there's got to be, you know, low value lands, there's got to be brownfields, there's got to be rooftops, there's got to be other places to put solar. And yes, there absolutely are. But if you add them up, there's still not enough to take care of the projected needs and the projected expansion of solar. So even with considering, you know, some of the alternative sites, like putting them on dumps, well, how many acres do dumps actually cover in the nation? Putting them on rooftops, yes, but not every rooftop has treeless, right? So there is going to be a push of solar into ag. And if that push is going to happen, as an agriculturalist, why not make that work for farmers in the highest and best way? Where are the opportunities here to leverage the investments of energy companies and energy subsidies into rural America and help American family farmers? That's the question to ask. So to answer that question, we have to know a little bit about crops and plants and how they function, a little bit about how soils function, a little bit about the water cycle, a whole bunch of stuff. But the first point is that plants actually, even way up north, I consider you up north from me, and I'm up north of the California folks. Even in your climate, a lot of agricultural crops, not all, but many, don't need 100% of the radiation they receive. They can do just fine with a little less, and sometimes a lot less. And that's due to several restrictions. There are things called C3 and C4 crops. C3s are older, and most of our crops are C3. Things like corn are C4, things like potatoes, C3. So all the older, heritage, really old crops are most of them are C3. And those are the family of crops that are less efficient at using light. So those are the ones we're thinking about. Now, if there's too much light on a farm, if there's more light than we need on this ag land and this crop, then why are the crops growing at their highest potential? Aren't they going to be under stress if you're giving them too much of something? Much like if you over fertilized a crop or overwatered a crop, it does them a detriment. Well, it is true. You can grow a crop you can grow lettuce in Arizona if you water it enough, right? And that's because plants sweat just like us, and they thermoregulate just like us through sweating. So if you're going to give crops more light, more energy than they need, what they do is they take all the energy that you give them, they just shunt out the excess through evaporation to cool themselves off. All right. So the extra sunlight hitting those crops is actually sucking up extra water from the ground that is totally non-productive to that crop. It's entirely used for heat regulation of those leaves. So, and here's the premise of the whole thing. If I know how much light the crop needs, and I start thinking of sunlight as a farm resource that can be managed, harvested, and sold, much like water can be managed and sold through water rights, then I become proactive in how I manage my sunlight to maximum benefit my crops. So can we design a system that takes off just enough sun so that the crops get exactly what they need and no more? And in that situation, they would be the most water efficient possible, leaving more water in the ground. And happy plants are tasty plants. I know that the growers might be rolling their eyes, but we look at things like nutrient content and so on in these, and productivity of these crops, and they are less stressed. They're having to do less regulation. So we see in certain circumstances extra productivity or increases in quality. And finally, the crops actually in agricultural activities do provide a service to the solar panels, in that the agricultural activities make the climate around the panels just a little cooler. And that can actually increase the energy production by increasing the efficiency of the panels. So the theory, and now I'm going to go through and try to give evidence of all of this, or summarize my evidence of all of this, is that this is a win-win-win-win situation where you have the benefit of producing more solar energy, you have the benefit of potentially higher quality and higher productive crops, and you have the benefit of having a more water efficient system. So this sounds almost too good to be true. Don't worry, we'll get to the bad news of it towards the end of the talk. So I'll give you all the good news first and then the bad news toward the end. So a summary of, we've been doing experiments for about 5 years. If you're a grower, you're looking at this and probably thinking there's no way in hell I could actually farm that tiny strip of land, and you're absolutely right. The solar arrays that we do experiments in are not designed for agricultural access. They're arrays where we got there too late. They were put in, and this soil, this ground that you're looking at, is the most fertile soil classification in the Willamette Valley. It's Chehalis soil. It's a class 1A, beautiful, deep, productive soil. But a solar array was put here. So this is also close to campus, so we grow crops in our experiments. Here you see some bush beans growing. What we've seen in our vegetable trials, so we've done tomatoes, beans, and some other crops, and my colleagues have done even more crops, is that they will grow just fine in these conditions. Partial shade, some of it is more shaded than others. You actually see, even in this picture, the ones all the way to the left are a little bit stunted compared to the ones over on this side, which are really lush. The lush side is the shady side. This is the full sun side, right? You can actually see most productive, little less productive, little less productive, least productive as you go across, where this is where we have the right balance of sun and water, and this is where we have too much sun for the plant. Okay, and when we do trials like this and we compare to even a completely open field, what we see are things like similar or slightly boosted productivity in irrigated systems. All right, these beans and the ones we grew outside the array, there was a slight increase in productivity on these beans relative to the field in the back here, versus a more increased, less modest increase in productivity relative to these beans to the field out there. The one thing that I find really interesting, and I know we're recording, so if you're watching this recording later, this is preliminary data and we're trying to verify it. But the most interesting thing is that the beans that we got from here had far more protein and vitamins and minerals in them than anywhere else. And it's too good to believe. So I have to really double check it. But there's also some obvious nutrient content changes in the beans themselves. Similar things happened with tomatoes. Now, pasture forage was even more interesting because we grew that in a totally dryland situation, not irrigated. And in the pasture forage situation, because this area gets so dry, nothing actually grows well there. And it doesn't grow very well in the late season in the open pasture anyways. But as soon as you introduce some shade, through the grazing season, we had almost double the productivity in our forage production in this shaded zone on this side, which was pretty amazing. Also, the water use efficiency of these crops dramatically increased when you start managing the sunlight. All right, so that's crops. Then we did grazing forage, so we might as well do grazers. These are our happy sheep. They look happy to me. We actually tested their happiness as well by looking at their levels of stress hormones. If you put sheep in a situation like this and you hire undergrads to sit and watch them 24 hours a day for weeks at a time and record their behavior, what you see is that the sheep, they actually preferentially eat the grasses underneath the solar panels for reasons unknown to me, but they do. And everyone had plenty of food here, so all the live weight gains were the same, statistically the same per animal as we go from the control area here in this pasture to the pasture underneath the panels. The big difference was that we could actually put a higher stocking rate there in the underneath the solar panels, because we did have that higher productivity. So we could put more sheep per acre underneath the solar panels, but the individual sheep themselves grew at the same rate as the individual sheep outside there. The stress analysis is ongoing. However, the stress seems to be much lower in the sheep that live with shelter than the sheep that live out in open pasture, and that shouldn't be any surprise. If you're in a really watertight situation, they drank a lot less water when they had access to shade. And I don't blame them. If I'm out in the solar array, I stand under the solar panels because it's much more comfortable there. So none of this is very surprising, but we can quite easily do grazing under solar panels, particularly situations where you might have a hard time getting equipment passes through. I still manage this field with equipment, but I have to use a 25 to 30 horse tractor to fit through. Okay, and we till with the 25 horse, and we seed, and we mow when we need to do mowing maintenance with that. So you can get equipment through here, but I got to admit, it's a total pain in the ass, and I would not want to do it at a production scale unless I had authority to design this for my access. And we'll get down the road to that as well in the future. Next slide. One of the things that people ask a lot about is pollinator habitat and what can be done to expand pollinator habitat. So Maggie Graham here, who was listed as one of the co-authors of this presentation, went out and spent a summer basically catching pollinators in and around solar arrays. She actually counted the number of blooms around, the number of times bees visited blooms, and the number of bees around. And we actually found that there's more blooms in the aisles where she's standing. The shade area had a lengthening growing cycle, so the bloom happened far later in the season there and was less pronounced. One of the things we were worried about was if the blooms were as attractive to pollinators, whether they're close to the solar panel or not. We were wondering, was there some electrical field that screwed up the bees, or even though there's a lot of blooms, they might not have a lot of pollen. But the bees didn't care, and the blooms didn't care. So the bees went to the blooms just the same. They had the same level of attractiveness. But this bloom delay actually is probably going to be important in the later season. So right around now in Oregon, and maybe even a little later, we get into this pollen desert time where there's not as many blooms going on, and the bees have less forage. I know the bees around my place are really starting to concentrate on the few things that are blooming. Whereas if you can take the blooms and delay them until the later season, that's the most vulnerable time for bees. Are we looking at wild carrots? That is wild carrot there, yes, which is a terribly invasive weed, is what I would consider it. Absolutely terribly invasive weed. But we are not in this array to manage the weeds. We are here to observe what's going on. Do you mind if I go into a deeper story about the planting? So, hearing no objections, because you're all muted. It's great. This site, which I won't name because I didn't ask them if I could name it, is actually was actually planted with native pollinator species upon installation. It was premeditated to be a pollen generating habitat and bee habitat. The germination rates were not as high as they anticipated for that, and there has been a tremendous invasion of some of these really aggressive weed species, and they're trying to think about whether they should philosophically manage this Queen Anne's lace and some of the other weeds, or if they should let it be. And pardon the pun, but yeah, this is one of those things about how the system evolves. You can't just plant something and forget about it. The system's going to change, and it's going to grow. So yeah, this is a very interesting solar array out there. But this is a recent publication. It's free. You can check out our bee data and our native and non-native pollinators and how that went. The other thing that we're doing, given that weeds study, is, I don't know about up north, but in Oregon, there's some pretty funky pharaoh looking solar arrays. Solar gets installed. The land is still really fertile, but it succumbs to weeds and becomes a source of weed pressure to the surrounding ag lands. And that's actually not very nice. So what we're doing here is we took a site that was feral for 5 years, and it was full of Himalayan blackberry and Queen Anne's lace and Canadian thistle and poison oak. Well, that one's native, but I still didn't want it there. And tried to rehabilitate it back so we could grow into it. So this is about restoration of some feral sites and how that might go. The bottom line of this is that plastic and tillage was the most effective. So mowing, plasticking, so mowing, tilling, and then plasticking was the most effective way to get the weeds under control in this environment. It was also the easiest to do, as opposed to some of the other things. Simply hitting it with some Roundup or even something harsher was not enough. There's enough in the seed bank for stuff to come back. So we needed to do a bit of insulation and a bit of ground heating with the black plastic to get those to get that started fresh again. So that was the bottom line of that one. If you're in a solar situation that's under high weed pressure, till it with a small horse tractor, black plastic it, that's your best bet. But I don't anticipate many people are going to do production ag in this area, but I do anticipate increasing social pressure to turn these type of solar arrays into habitat for bees moving forward. All right, so we've got, it's good for, our data show it can be good for pollinators and blooms. It can be good for vegetables. You can restore land that was taken out of production back into production, and that we save a significant amount of water, that the sheep were just fine and happy and just as productive grazing under the solar panels. So there's a lot of good stuff that's going on. I think what our lab is probably the most well-known is not the individual studies, but how we put things together into context. So let's talk about that and what all this means. So I alluded to this before. Hey, it's the first plot of the presentation. But there is a reason why ag land is so attractive to solar developers. And that is if you do a global assessment of PV solar power potential and then rank that potential by land use type, croplands come up number 1. So all else being equal, on average, if you had 2 sites, say croplands and barren desert, you are more likely to get higher returns on cropland from an economic perspective than you are on barren lands. Okay, so there is an economic driving factor behind this as well. And it's something we really have to think about. And this is where I say, you know, what is farming but solar harvesting? It's just that a leaf has an integrated energy storage mechanism, which we call food. And yeah, we had a head start as agriculturalists, so we already got all the great places. And they're trying to get into our places now. So let's make the best of it that we can. Okay, so I'm gonna put some arrows on this. This plot is, it might be a confusing plot, but I'm gonna go through it. So there's a lot of ways you can come to a conclusion that agrivoltaics might be a good thing. The plot on the previous slide is one of them. The data that the experiments that I talked through is another one of them. This is one that we're going to take a journey through water management and how, even if you look strictly through the eye of water management, the dual use technology is probably something you want to look forward to. So here we go. We know that irrigated land is much more productive, and it's a very important part of a climate adaptive future. We also know that there's three major types of irrigation. There's micro irrigation, that's drip tape, micro bubblers, micro sprinklers, etc. But most people think about this as drip. There's sprinkler irrigation that includes things like solid sets, overheads, wheel lines, etc. And then you have surface irrigation, which is basically all the flood types. Least efficient, middle efficient, most efficient. There's also, in terms of water use, there's also productivity increases in the literature. So if you switch from surface to micro irrigation on your farm, you usually get a bump in yield as well, just to the extra tightness of the water management. So there is enough data out there on the efficiency and productivity of these three classes of irrigation systems to project what the global food production would be if we tried every combination on a global average mix of these three. Okay, right now we live here, and how you read this is 20% micro, 70% flood, and well, the balance of that, it goes 20% sprinkler. You follow the parallel line down, 20% sprinkler. Quite a lot of surface, and about 5%. Where is my 5% of micro? So we're basically down here. We're mostly in surface. This is the 8,000 year history of agriculture. So in 8,000 years, we've explored exactly from all flood irrigation to our current mix of flood, drip, and sprinklers. So all the rest of this is unexplored. However, if we go into other parts of this technological space, we grow more food, which means we can support more people. So the colors behind this is the supportable population of the earth, given that technological mix of irrigation technology. So if I go 100% micro up here, that's the most efficient. I stretch the water the most, I can feed the most people. If I go back down to 100% surface, that's the least efficient. That's what we were doing in 6000 BC. That's gonna feed the least people, do you see? And then everything else is a combination thereof. And what I've done is I've taken the liberty of putting the current projections, the current population and the projections of climate into the future. Notice that there isn't a line after 2050. That's not because I didn't want to put one there. That's because there is no technological combination between these irrigation technologies that gets us to enough food to feed the 2060 population projection, which kind of sucks. Also notice that if I take our current level of technological progress today, 2030, 2040, 2050, the distance we have from where we are to where we need to be increases. So not only are we not making it in terms of water, we are actually falling behind in our current rate of technological adoption and innovation. So that's not a good sign. But, you know, my dad didn't raise me to give up on things, right? So this is not, what this is it is a call to innovate beyond the box, right? We've got to think literally outside of this triangle and think of new ways to manage water. All right. So what are those ways and how we can do that? Well, agrivoltaics save a lot of water. Intensive greenhouse production saves a lot of water. We can eat less. That's actually one of the scenarios. We can rely on ocean, produce food more. We can actually not consider a changing climate and not have to increase our irrigation to take care of that. But all of those change the trajectory of what this plot looks like. So what I do on the next page is I take these distances and I plot them out. And what we want to see is we want to see these gaps close over time. All right. So let's look at one of these. This is the one that I just showed you. That gap increases over time and eventually hits our technological limit. This is a no-no. This is our current course. We run out by 2060. We don't want to be on that. Okay, so this one B is if I wave my hands and say the climate is going to stay as it is now, we solve climate change and we never have to worry about it again. That's exactly how much change you get in terms of our ability. We still are growing out, yes, and we still hit the technological limit. Solving climate change isn't enough. If we go and change our diet such that we take 10% of calories from quote unquote alternative sources, and this is a polite euphemism for saying looking at things like insect proteins and other ways to get calories that are not current agricultural practice, that actually gets us a little farther out before we hit technological limitations, but doesn't get us there completely. If we move sort of all vegetable production and high value production into large scale greenhouses, that actually has the biggest effect out of anything. You know, the power of agriculture is greater than climate in terms of sustainability. Isn't that amazing? What this does is it keeps us from reaching the technological limit by 2050, but it doesn't get us to the green zone, which is where sustainability would happen. It doesn't pinch this off to zero. The agrivoltaics situation is this one here. And it's the very first one that we actually see some kind of bending back towards pinching together towards sustainability by 2050. And it's the first one where one of the scenarios out of the 20 million we run actually got to sustainability. It's that 1 in 20 million chance of getting sustainability if we just do agrivoltaics, where all these others are zero. And then if we take agrivoltaics and we start to combine it with these things, we get sustainability. So what seems like a major problem is just a clarion call to innovate and be, try to be more productive and use our resources at a higher level, and that leads to more sustainability, both in terms of water, energy, and food, but also economically, because you have the extra source of income. Now, this is a simple plot, but I just did the thought exercise. We were thinking a lot about the current money printing environment that we're in terms of stimulus and so on. So I asked the question, this sounds like a good idea. How much investment in rural America would it take to reach some of the Green New Deal objectives? And it turns out that about 1% of farmland in the US would achieve the sustainable energy targets in the Green New Deal. It would require $1.2 trillion of investment into rural America and American family farms, creating 20 million jobs. And on top of that, because of going to sustainable production, we also address 11 out of the 13 other goals in the Green New Deal. Rural America is part of the solution to the situation that we're all facing. And I believe that investment in rural America is the way forward. Now, of course, these are money positive systems, so there will be a return on that investment. This is not just going into a sinkhole and going nowhere. But that's the upfront cost to do it with a wand of your hand. And by the way, we're spending that much on other things these days. So an example of how we might address other Green New Deal aspects here in rural America with agrivoltaics. Let's take a look at the one where they want to electrify transportation. Well, the big problem with transportation electrification is something called range anxiety. And if you've ever driven across the great American West with a half a tank of gas, you know what this feels like, because you don't know if you can get to the next station before you run out, right? And if you're in an electric car, that is even more the case because there's far fewer charging stations. There's even a bigger problem in the wide open spaces in the rural areas, because the electric infrastructure in the rural areas is insufficient to transfer enough energy to those areas to charge the cars. The energy has to be generated locally in the rural area. So we asked the question, hey, can agrivoltaics in Oregon provide enough density of charging stations in rural zones such that range anxiety would be equal to or lower than the current gas-fueled system? And the answer is yes, we can. And we can meet it quite easily. So we actually did a very strict, take every intersection, look around at a certain radius. We partnered with the American Farmland Trust and used their data layer to identify farmlands. We partnered with the DOT and they gave us all the traffic data. They gave us all the road data. We partnered with the USGS and they gave us things like if there's endangered species or tribal lands or heavily forested or other attributes that would make it undesirable for solar. We laid all those on top of each other, and all of these lands in the blue were potential candidates for agrivoltaics for charging stations. And what is needed is we just took this, I guess it's kind of salmon color here, is the closest set of land to the charging point to fuel that station, right? And 84% of all intersections in Oregon could be completely energized with agrivoltaics if we wanted to do it. Now, of course, there's all kinds of problems with this. What if the landowner doesn't want to do this? You know, what if there's laws and permits and all kinds of stuff? I get it. But what I'm saying is, if we are serious and if there's investment in making these things happen, why not invest in farms and help farms become more sustainable? All right. So AVS can absolutely be a solution here, and that totally meets yet another Green New Deal target. Okay, and I don't have a clock here, so give me the high sign if I'm really too late. All I see is my presentation, and I feel like I'm going over time. But I can stop here, or I can tell you the question I get after going through a lot of this is, why the hell aren't we doing this? This seems like a great idea. Well, I've been trying to do this. So here in Oregon, I am attempting to build a purpose-built agrivoltaic dual-use farm where all the energy needs of the farm are supplied by the solar array and creates a revenue stream for the farm by selling the excess. Designing the solar array such that there is enough space to get all our harvesting equipment and planting equipment through, and instrumenting it with scientific equipment. And I did not pull strings. We decided to go through the process as you would have to go through it as a grower, just to see what a pain in the butt it would be. And I can tell you, there's many pains. Thank you, 5 minutes. There are many pains. And here's a list. Here's where we're doing it. It's going to be at the Northwest North Willamette Research and Extension Station. We've got about 6 acres here that we're gonna turn into the sustainable farm of the future. And we're breaking ground this spring on this project, and we've got it now fully permitted, fully insured, fully bonded, fully funded, and we are placing orders on solar panels now. Just had a conversation today about getting the order of our solar panels in. And I started this process 5 years ago. All right. There are a litany of hurdles that you'll have to overcome. The first is financing. Depending on what you want to do, whether it's a behind the meter or a in front of the meter installation, we're actually doing an in front of the meter installation, meaning that we are selling our electricity for profit to people. We are using a program, we're part of a program in Oregon called the Community Solar Program. This is probably the best program that I found to partner with for these type of projects. The model works just like a CSA, but for electricity. You have subscribers to your electricity and you sell to the people directly for an increased price, and that helps the economics. All right. I don't know what the laws and regs are in Oregon, but I know that community solar is a nationwide program, and it also builds a lot of goodwill to our neighbors because you're providing low-cost power to your neighbors, basically anybody around you who wants that. So the first thing that took me a year and a half to figure out is that I should stop asking the federal government to help me with this. I should go to the private sector, and then I figured out that the community solar was the best partnership for us. These are out of order. The next most important thing was permitting and insurance. You can imagine that the insurance conversations were spicy. Trying to figure out who is liable for what. And, you know, this is an interesting project because the county owns the land. OSU has a long-term lease, and we have a private entity through the community solar project. So there's three: a government, a university with both have massive expensive lawyers, and an energy company that actually had less lawyers, which was interesting. And they had to come together and come to an agreement about basically playing the what if game. What if Chad trips and bumps his head on the solar panels? Who's liable there? What if a grad student doesn't receive sufficient training on tractors and runs over the solar panels and kills them? What, you know, they ran through months and months and months of what if situations. But I will tell you, the end of this 6-month process with, I don't know how many dollars in lawyer fees were spent because they were not my lawyers. But the bottom line agreement between everybody was insure your own stuff, agree to mutual indemnity, and whoever has the keys and control of the gate has to do the personal liability insurance. And that's, I mean, there's a 150-page document to explain that, but that is the basics of it, right? Solar panel people insured their solar panels. We insured our farm equipment, and the university wanted to control access to the site. So they've got to pay for liability, personal liability, because they're the people letting people through the gate. Done. All right. I don't know if that will work for everybody, but that's what worked for us. Laws and permitting. In Oregon, we are extreme land protectionists. Solar projects are prohibited on certain classes of soils and limited on on other classes of soils. There's an extensive permitting process that involves state and county officials. And we went through that full permitting process, through the public comment period, through the whole thing. And that process took about a year to get through. This can be done a lot faster. If I had to do it again, I did not understand exactly how to do it because I'd never done it before. So if you're in Oregon, I can help you out. But I would strongly advise you to, talk to your county officials ahead of time, because they're the ones that ultimately make the decision, and you want them to be on your side. You want your county fighting for your success. And that was really a key factor for us in making that happen. We did laws and then contracting. Right now, if I could get solar panels to us, we could install today. But we have tons of logistical problems. The price of steel keeps increasing. We're fighting some of these inflationary problems, and that has been a quote unquote fun time. But we've gotten there, and that came through basically a bank loan that the private entity is taking on, plus some equity investment and tax credit investment that they receive. And plus the subscriber money, and that pays for everything. So we didn't have to pay for the solar panels. We're able to do all of our research. I got to design it the way I wanted to, and we'll break ground in the spring. So essentially, and I just did something there. What I would advise you to is, if you're interested in this, talk to your county, make sure they understand what you're trying to do, and make sure that it's something that they would support. Consult with a lawyer, particularly one that's really good in insurance. You're gonna want, if you're doing this dual use thing, you're gonna want that help. Question: we have solar on the farm during the summer. We sell excess, but around October, March, our production doesn't meet demand in December. Okay. Long-term storage doesn't seem viable in the near midterm. Perhaps using trackers and in-field placement for optimum is the only solution. Not easy, but I'm curious as your thought on how to reduce seasonal production gap in the next 5 years. I've got a funny solution that I'll share with you in a second, because I'm trying to do this on my personal farm. I won't do this on the research farm because it's a little too wacky, but I think it's going to work for us. So yeah, talk to lawyers, make sure everything is above board, and be insistent that they're coming on your land. They're the ones that need you. They have to be able to accommodate your needs, right? And they will, because they really need to get access to land these days. So you are the ones in the position of power. Make sure that you know that. In terms of meeting the productivity gap, what I'm going to do on my farm, and this may or may not work for anybody, is I'm installing, and my plan is to install so that we produce exactly the amount that we would need in the low time and overproduce in the summertime. Okay. And then load level with cryptocurrency mining and use that as a source of income. So that's what my plan is. It's a little bit off the wall. I know, Christine, it's a little bit funny, but it is a way. There are other ways to generate revenue from electricity than selling it directly. All right. And that's one of the things I'm going to explore. And you may want to look into those things as well. If you can't do that, then your system is probably what you want. You're gonna want to buy your shortfall in the winter. That's when electricity is cheaper anyways. So that might not be a bad situation. Let's look at is there a trade-off optimizing EV production versus ag? Yes, there is. If you optimize EV production, you're going to end up with no access to your ag land. The trade-off really is access versus density of panels. All right. So you're going to want more access. They're going to want a higher density. There's two ways to get access, basically, is you can spread them apart farther, or you can lift them up. Now, lifting them up, you can keep them just as close together because you can get your equipment underneath, but there's extra steel cost in lifting them up. So that's the trade-off there. There's a capital investment up front, buying the extras post to raise it up. Spreading them apart reduces the production per acre, but that might not be a problem if you have enough acreage to satisfy the needs of the transformers and everything that you have. Usually what we have, and this is another thing I tend to say, is that ag can overproduce anything, including electricity. Usually the problem we have is that the wires are not strong enough to carry the power away. Not that we don't have enough land to make that. Time to wrap up so we can have some question time. Yeah. I hope I seamlessly slid into questions. Watt per AC AVS installations, we're at about $1.50, which is like 20% more than 20 to 30% more than traditional.
Before we totally go into question time, I want to introduce Tessa here, and so.
Oh, Tessa, I'm sorry, I took all your time.
You didn't take all our time. We're doing good.
Okay.
But I want to give Tessa some time here before we get into the full Q&A portion. So Tessa Ormenyi is a residential electrician on Orcas Island and works for Rain Shadow Solar and Energy Solutions. And Rain Shadow Solar has been designing and installing renewable energy systems throughout the Northwest, but primarily in the San Juans since 1989. So they do commercial and residential renewable energy systems, solar voltaic, battery backup, and they've worked with some farms, including working with the USDA Rural Energy for America program, the REAP grant that we heard about earlier. So I'm going to hand it over to Tessa.
Thank you. Thanks so much. And I've learned lots. Thank you, Chad. So Rain Shadow, let's see, we do mostly, what's the new lingo? I'm coming from my electrician land. We do mostly behind the meter installs. So grid tied installs primarily, though we do a number of off-grid installs. So you want to get water out of your pond to water something else. And we put a little solar and some batteries and a pump to get water out of your pond. We do all sorts of things. We install electric vehicle chargers more and more nowadays. And the lithium battery backup market is exploding, and it's changing rapidly, and it's a little exciting. So most of our installs are really small compared to kind of the scale that we saw in a lot of Chad's photos, and the scale that we're talking about is going to happen over the next few decades. These are for private businesses. These are for homeowners on the islands. And most of our installs are on roofs. Most of our installs are on farms, have also been on roofs, pole barns. Where do you put the hay to keep the hay dry? Cover it in solar panels. And one of the issues that we do face quite a bit is the size of the wire in the ground, and can it handle how many panels we can put on the roof. Let's see. So I'm just going to give a little bit of an overview of kind of what I do, and then talk about the price. I'll try to give an idea of pricing and the incentives landscape in Washington. I am a little bit, out here on the islands. I live in a bubble out here, so I can talk to what I know, and I'm sure there's things that I'm missing. So our utility and many local utilities have net metering. And so when you install a grid tied solar array, your meter will turn both ways. And basically that means that in the summer months, when your roof is likely producing more and your house is consuming less, you are credited that power that your roof produces at a 1-to-1 rate, so that in the winter months, you can use that electricity that you produced in the summer in the winter when your roof is producing less and your house is likely consuming more when it gets colder. And these net metered grid tied systems, I want to make it clear, it's often a little bit of a point of confusion. Solar doesn't necessarily mean that when the grid goes down, you have power. you need a battery backup system connected to your solar in order to then have power in your house during an outage. And outages out here on the islands is quite common. So we're seeing these battery backup systems more and more, and get lots of questions about them. We install some ground mount systems like we saw, like the photos we've seen. We do, I would say, a handful a year. And one of the new things that we've started doing in a few installs is actually integrating them into fencing. So a big long line of solar panels will be, say, the north side of a fenced pasture area. And so trying to think about, we are trying to think about a little bit, just on the small scale at a small parcel of land, how it can be used, how it can be dual use. These ground mount installs sometimes involve a lot of concrete. Sometimes we're going into soil, but mostly on the islands, we're going into rock. And that involves an engineered system where we pin to the bedrock, epoxy rebar in, build footers, pin the steel structure to the footers. We also use these, if we hit soil, if we have a good 4 feet of topsoil, we use these ground screws, which can be driven with an auger attachment connected to a tractor or a skid steer. There's a pull and a shear test on them. And then the steel pipe structure, 2-inch galvanized Schedule 40 pipe slides into these, and it's pinned into these ground screws. And that they are definitely more removable than several yards of concrete if and when the system meets its decades, its 30-year lifespan. We take into account shading very seriously. A shaded solar panel doesn't do a whole lot. So that means trees, that means other fencing that could be in the way, that means weeds, and that means raising things above what native grasses could potentially get to, hoping canary grass isn't right in front of your solar array if it's a ground mount. And at the farms that we've installed ground mounts at, or at any installation that involves a ground mount, there's trenching involved. And trenching, the National Electric Code requires conduit to be 18 inches deep, and we often put it quite a bit deeper so that tillage or planting trees along a fence line later doesn't accidentally cut off your entire solar production because you hit that line. There is a requirement that we have come across more and more, that you have to fence your solar ground mounts. And that's a safety concern so that kids who try to climb on your new jungle gym don't pull at the wires and electrocute themselves. It can also be a safety concern for animals, nibbling at wires, horns, pulling wires down. But there are ways around it. We have figured out a way to attach the fencing directly to the underside of the solar panel so that the wires are kept up against the underside and don't end up hanging down. And then you can actually get a mower underneath, and you don't have to get in and around this fencing that gets put around your ground mount. Let's see, what else? Pricing, let's see. So I can talk to our island, San Juan County Islands installations. We are looking at the high 2s to low 3s a watt. So that's about like $2.80 to $3.20 or so a watt. And a typical system that we put in is about an 8,000 watt system. So that's 8 kilowatt system. That's about 20 solar panels. We put in all sorts of other systems. We put 2 panels on a little shed roof to pump water out of your pond. And we just put 125 panels on the co-op in town. On their roofs. So we do all sorts of systems around that. But for an 8,000 watt system, that's looking at about, what's that math? 21 grand to 25 grand. And the payback for our utility is, so this is all dependent on how much you pay for power. And the payback that we usually look at is between 10 to 12 years. The Washington state incentive was a program that dried up 2 years ago, just before COVID, I think. And it reduced that payback period by quite a bit, and we're hoping that it gets renewed soon. But currently you don't pay sales tax on solar systems, and there is a 26% federal tax credit, which for people or whomever is interested in battery systems, if a battery system is coupled with a solar system, that battery system cost is included in that 26% federal tax credit. And then Faith mentioned this REAP program. So it's the USDA's Rural Energy of America program. We've used this program to, help finance systems for rural businesses on several islands now, one local farm on Lopez, actually. It can cover 25% of solar installation costs, and that brings down the payback estimate a number of years, and that's really exciting. I think that's kind of just a brief summary and overview, and I'm looking forward to everyone's questions and hearing more about everyone's thoughts. Thanks so much.
Awesome. Thank you so much, Tessa and Chad, and let's open it up to questions. So let's see. Chad, did you answer what is the approximate money for WAC versus for AVS installations? You're muted again.
You'd think I'd done this before. Yeah, so I quoted a price that was quite a bit lower than Tessa, and that's because we're talking about economies of scale here. So, you know, our conversation today was, you know, we have to size it so it's exactly 2 semi trucks. That way, that's the cheapest way we can get panels, right? And when you get up to the big size, you're gonna get price breaks on. So that's just the difference. When I'm talking, you know, $1.50, $1.60, that's just the difference between when you're buying by, you know, the ship load versus the just a few boxes worth. Is there a backlog in solar panel orders? I don't know what it normally is, but we're looking at least 3 to 4 months right now. I don't know what you are, Tessa, but our supplier was kind of like that.
Yeah, we there's a bit of a backlog, but during COVID or there was a lag, but we did experience, actually we had a larger problem with electrical parts, fittings, components, conduit. Getting the actual wires in the wall or in the ground was harder than actually putting the solar panels up.
Yeah. Chris asks, how big is the system at the research farm in watts? So interesting constraint is that the community solar program can't be larger than a certain amount of wattage. So that was our upper constraint on how big we could go. And we just reshuffled the design, but it's right around 400 watts. It's not huge. The only reason we're getting the economies of scale discounts is from working with producers and kind of piggybacking on larger orders. So that's been something we've had to work on to make to squeak through with the financing that we have. So I would say you're not going to get commercial discounts at that size. You're going to have to go pretty big for them to care enough.
I'm curious, Chad, do you have any, from the work that you've done and looking at different communities, do you have any kind of communities that you really look to that you see are like doing a really great job of their kind of policies around around agrivoltaics or around siting solar on farmland. And this could also be for Brandy too, from work that American Farmland Trust has been doing.
I think the East Coast has been a little more proactive on this one, particularly Massachusetts has been a leader. You know, is it Minnesota that put out the bee guide? There's been some, you know, central north US states that have been pretty good. Colorado has been interesting. There's this, here's a really interesting paradigm is there's a U-pick farm that's gone agrivoltaic. So they don't have to worry too much about the harvesting equipment. And because of that type of agritourism approach, it was kind of a hook to get more tourists in there. How many co-op clients do you have with your farm? Asks Abe Gates. So it depends. No one subscriber can take more than 40% of the electricity by the law, and a certain fraction of it has to go to disadvantaged communities, churches, and schools. So if we say have one anchor subscriber, and we do, that's Oregon State, they're going to buy 40% of the power. And then the rest gets broken up. I'll have to ask, it's going to be a hazard of a guess, but it's in the kind of 50-ish, 50 to 100. And that can be, you know, that big of a number because some people will subscribe for more or less. Any local regulatory conversation about this yet? Would current use program allow agrivoltaics on farmland? This one, I don't know for Washington. So I'm going to punt on that one, Christine, and hopefully someone else can answer that for you for your local growers. If you want to know Oregon, I've got you. As our farms are rather small and pasture land is often locked into forest resources that may limit horizon to horizon solar capture available, is there a watt to acreage size that would be beneficial or not? I would have, so this is a very local question, right? It kind of depends on, I can do that calculation if I know how high the trees are and I know how big your lot is and I know what the slope of your land is. So there's a way to calculate that, but I you know, it's such a local question. I can't say whether your particular farm would be. I'm sure there's a possibility, but there's also a possibility otherwise. And I'm sorry, that was super shady as an answer, but I just can't for sure know that one.
Really interested in hearing from Tessa on that previous question in terms of local regulations and you know, what that landscape looks like in San Juan County.
Yeah, our county is very friendly to solar. However, we don't install big farms. So solar on private land and it doesn't take up the whole field, right? So, but we work really closely with our county, with all of our installs. They're all county permitted and they're all state inspected. So county inspected. So sorry, yeah. And then in terms of the watt to acreage size as well, I was going to say as well that there are ways that I can easily model that for your specific acreage right now online using some LiDAR data, but it's very hard to say off the top.
I will say Chad mentioned a 400 kilowatt limit on community solar projects. Is that correct? And I think in Washington right now, it's currently 100.
Oh, it's smaller. Okay.
Yeah. Mm-hmm.
All right. One of the things that we explored and actually got approved for, if we wanted to, was to have 2 community solar projects coincidentally located next to each other to get up to almost a kilowatt. A megawatt. But it turned out that the spacing and science didn't work for that. So I don't know if that's a permittable up in Washington, but that was a way to get bigger systems if you wanted to. the ARC is researching the issue. Does not have any recommendations at this point. Would love to hear from farmers what you think. Not sure the current usage.
use.
I'll look into it.
Yeah.
Okay, so that's Faith.
That was, I just put that out there, Chad.
Yep. So
It
I'm reading
wasn't really a
Faith's answer.
question.
Yeah. Thank
Yeah.
you, Faith.
Yeah, and I guess I'll just say, and if you're in San Juan County, the ARC, the Agricultural Resource Committee is definitely, we're in this conversation and we're researching, and you're in the ag community. We would love to hear from you, and I'll put my my info in the chat. So love to hear your thoughts.
Perfect.
So, and I don't know how current use and agrivoltaics mix, or if there's any concerns with having agrivoltaics as far as the current use program. I'll look into that and try and get that information out.
Yeah. I think that most growers are gonna want to go behind the meter to test the waters at least first, and work with Tessa on that. And the stuff that I've been looking into, the large scale production, it does require a lot more, pain and suffering to get to the point where you can get something that big going. But there is a potential profit on that. Oh, Addie has the link to the policy guide. Thank you, Addie.
Well, I don't see any more questions coming in here. So, and it's coming right up on time. So before we totally wrap up, I want to say, so Kate is going to drop into the chat both an evaluation for the webinar and also a Google Doc that has a bunch of different resources on it. So go ahead, and you want to click on those links that are in the chat. You can just have the link to the Google Doc, and also we really love evaluations. So please take the time to fill out the evaluation. It's always helpful. And this has been an incredibly stimulating conversation, and I have learned a ton and feel like I have a lot to think about. And it was a really lovely, just between Danny and Chad and Tessa, I feel like you guys just like nailed it. And like, here's the, broad overview, and like down into the nitty gritty, and all of your research and deep thinking that you brought to your presentation, Chad. I just really appreciate it. So in bringing this to a close, I just want to say thank you. Thank you, thank you. And also to everyone who participated, please do reach out if you have, thoughts or questions, especially if you're in San Juan County and thinking about these issues that ARC would definitely like to hear. So thank you, and have a lovely evening. And thank you to the sun for food and energy.
Yeah. Thank you, everybody. And thanks for the invite. It was awesome.